Hello guys, today we are going to learn about inverse Laplace transform. Now what exactly is inverse Laplace transform? Let's take an example. If y is equal to x, then that also means that x is equal to y. This is nothing but what happens in inverse Laplace transform. We know that Laplace of 1 is equal to 1 by s. So this also means that if we try to find the inverse Laplace of 1 by s, that should come to 1. And that happens. Laplace inverse of 1 by s is equal to 1. Similarly, we know that Laplace of e raised to minus at is equal to 1 by s plus a. Therefore, Laplace inverse of 1 by s plus a is equal to e raised to minus at. The difference comes in when you try to find Laplace inverse of sine functions. So Laplace of sine at is a upon s square plus a square. But Laplace inverse of 1 upon s square plus a square is equal to 1 by a sine of at. What's the change? This. Here a is present, but when we try to find Laplace inverse, 1 is present here. Okay, so please note that. With cos it doesn't happen. We know that Laplace of cos at is equal to s upon s square plus a square, and Laplace inverse of s upon s square plus a square is cos at. But when we try for sine h at, then we know that Laplace of it is a upon s square minus a square, but Laplace inverse of 1 by s square minus a square is equal to 1 by a sine of h of at. So this is all about the Laplace inverse transform. Okay. Now to find the Laplace inverse, there are various methods. The first method is direct method. This direct method is also called as method of standard results. So what happens in this method is we use the standard results which we just saw to calculate the value of Laplace transform. Let's take an example. Two by s plus 1 by s cube plus 1 by s plus 4. If we want to find the Laplace transform of Laplace inverse transform of this, then we know that Laplace inverse transform of 2 by s plus 1 by s cube plus 1 by s plus 4 is equal to, again this can be broken, Laplace inverse of 2 by s plus Laplace inverse of 1 by s cube plus Laplace inverse of 1 by s plus 4. And by solving this, we know that 2 will come out for the first one, so we will be left with Laplace inverse of 1 by s, and this comes out to be Laplace inverse of 1 by s is 1. We saw that. So this 2 into Laplace inverse of 1 by s, and Laplace inverse of 1 by s is 1, so this becomes 2, plus Laplace inverse of 1 by s cube, this will be t square by 2. Okay, how? You can find it out from the formula. This is a standard formula again of t raised to n in Laplace, and this last one becomes e raised to minus 4t. So final answer is 2 plus t square by 2 plus e raised to minus 4t. Okay, so this was the direct method. The second method that we have is called as method of shifting or the shifting theorem. We saw the shifting theorem in Laplace 1 also, that is in Laplace transform. The same shifting theorem applies in Laplace inverse transform also. So what changes is that we know that Laplace transform of f of t is equal to phi of s. Then Laplace transform of e raised to minus at f of t is equal to phi of s plus a. So Laplace inverse of this, that is phi of s plus a, is equal to e raised to minus at Laplace inverse of phi of s. So what exactly is happening here? This f of t which we had before becomes phi of s, like we have to find its Laplace inverse and multiply the answer by e raised to minus at. So I had given you the trick before and the same trick applies here. Before I had told you in the first one that wherever s is present, you have to change it by the power which is written here. Suppose if it was written as e raised to minus bt, okay, so you had to write s plus b, and if it was written as e raised to bt, then you had to write s minus b. So wherever s was present, you had to add or subtract b. Here when you solve this type of question, whenever s is written with something, okay, in question it will be written as 1 upon s minus 6 the whole square plus 3 square. If this is the form you can bring it, then you know that e raised to, it will be e raised to 60, because 6 is same as b which we had used here. Okay, 6 is same as the b which we had used here. So let's solve a question based on this, then you can understand it in a better way. Suppose you are given, find the Laplace transform of s plus 2 upon s square minus 4s plus 13. If we have to find the Laplace transform of this, what we can do is we can write it in this way. This can be changed into s minus 2 the whole square plus 3 square. Okay, so remember the trick. You have to bring something with s, and the second term must also be a square, because all the formulas which we have seen, okay, only this has power 1, otherwise all others have power 2. So you have to bring it in power of 2. That is the constant, you have to bring it in power of 2 or square. So this becomes, so this is now, you know, by changing this we got this. Okay, now further what we can do is we can write it as Laplace inverse of s minus 2 plus 4 upon s minus 2 the whole square plus 3 square. Now why we did this? Because if you see the formula again, you will notice either you should have 1 in the numerator or you should have the same s in the numerator. Okay, now bringing 1 here is possible but very difficult. You have to divide each and every term by s plus 2, which is not suitable. So the other option that you are left with is to have the same s above and below. The formula for shifting theorem will be given in the description. You can check it out. So this becomes, now it is minus 2 here with s. So the trick I told you is whatever is with s, you should write it out. If it's minus, you have to write plus. If it's plus, you have to write it minus. So it becomes e raised to 2t into Laplace inverse of whatever is left, that is s plus 4 upon s square plus 3 square. This minus 2 part went outside. Okay. Now finding this is easy. What we can do is split it into two parts. First find Laplace inverse of s upon s square plus 3 square plus Laplace inverse of 4, which is nothing but, no, we write it 4 s square plus 3 square. Now this becomes e raised to 2t Laplace inverse. Now this is s upon s square plus 3 square, which is again the standard form of cos at. At from here a is 3, so this becomes cos of 3t plus, now we know that we cannot find the Laplace of a constant number, we can take that out. Okay, so similarly Laplace Laplace inverse also we can take the constant out. So this becomes 4 into Laplace inverse of 1 by s square plus 3 square. Now 1 by something makes us remember about sign. Either it can be sin 80 or it can be sin h of 80. Okay, but since it is plus in the denominator, so we will use this formula, which gives us 1 by a into sine of 80. So that means this becomes e raised to 2t in bracket cos 3t plus 4 into 1 by a, which means 1 by 3 into sine of 3t. So this is the final answer, that is 4 by 3 sine of 3t. And this is how you find Laplace transform, Laplace inverse transform using shifting theorem. The third thing is by partial fractions. So I will directly go into the question. Suppose you are given a question like this: phi of s is equal to s square plus 16s minus 24 upon s raised to 4 plus 20s square plus 64. If you are given like this and you have to find its Laplace transform, if you go by the shifting theorem, if you try to apply shifting theorem, you see that it is a quadratic equation in the numerator. To solve it and separate it into algebraic expressions without the square is very difficult task. So we will go by partial fraction. So what happens in partial fraction is, first you have to segregate the denominator. Okay. So this, if I segregate it, becomes s square plus 16s minus 24 upon s square plus 4 multiplied by s square plus 16. Okay. Now what I can write is, this whole thing can be written as as plus b upon s square plus 4 plus cs plus d upon s square plus 16. Okay, since it is in the since denominator is in quadratic form, therefore we have to take two terms, as plus b, and here also denominator is quadratic, so cs plus d. Okay, now how did this come out? This came from this original question, so we will write the original question this side. Now what we can do is take this denominator on the other side. Okay, so it will become s square plus 16s minus 24 is equal to as plus b upon s square plus 4 multiplied by s square plus 4 into s square plus 16 plus cs plus d upon s square plus 16 into s square plus 4 into s square plus 16. Cancel out whatever you can find similar and you are left with as plus b into s square plus 16 plus cs plus d into s square plus 4. Now whatever is left on this side, let's write it down. Now the trick to find the values of a, b, c and d is numerous, but people get confused. They try to find relation between a, b, c and d. They try to make equations, but I give you a simple trick. Whichever bracket is associated with s, you have to make it 0. Okay, wherever s is present, you have to make it 0. Okay, but one by one. Why one by one? Because if I want to make this bracket 0, I should make sure that this doesn't become 0, otherwise the whole equation will become redundant. Okay, so if I have to make this bracket 0, what I can do is I first take s is equal to 0. A will get eliminated. Okay, I will be left with only b and d, and then I can find the relation between b and d, and then second step what I can do is make this whole thing 0. How to make this whole thing 0? Substitute s square is equal to minus 16. So wherever s square is present, you have to make it as minus 16. So minus 16 plus 16 will become 0. So this whole thing becomes redundant. And here we can find the relation between s and like c and d. So you will have many equations in terms of a, b, c and d. By solving them, you will find the answer of all these constants. Okay, so I'll write the steps. I won't perform it here. Steps: put s is equal to 0. Second step, put s square is equal to minus 16. Third step, when you want to make this 0, put s square is equal to minus 4. Don't substitute the value of s, only substitute the value of s square. Okay, by doing this you will find the relation between all the constants, and then you can solve them simultaneously to get the answer. For any partial fraction you can go by these steps. Try to make the bracket 0 by substituting s in such a way that it becomes 0. Okay, after solving all this, you will get the value of a is equal to 4 by 3, b is equal to minus 7 by 3, c is equal to minus 4 by 3 and d is equal to 10 by 3. Resubstitute these values into the partial fraction which we wrote before. So phi of s becomes 1 by 3 into 4s minus 7 upon s square plus 4 minus 1 by 3 into 4s minus 10 upon s square plus 16. This 1 by 3 is nothing but the upon 3 which each and every constant had, so I took it common. Okay, now we have to find Laplace inverse of this whole thing. So again what we can do is first write 1 by 3, then break 4s by s square plus 4, Laplace inverse of this, and minus Laplace inverse of 7 by s square plus 4. Okay, find this. Okay, I have broken this one. Now what I can do, write 1 by 3, this 1 by 3 here. Now again break this one, so 4s by s square plus 16, Laplace inverse of this, minus Laplace inverse of whatever is left, 10 by s square plus 16. Okay, now this 4 can be written as 2 square, this 16 can be written as 4 square, this 4 and 10, this will be taken out of Laplace because they are constants, this 7 and 4 will also be taken out, and by solving all of this and then using the standard form, you can find the Laplace inverse of this whole thing, which comes out to be 4 by 3 cos of 2t minus 7 by 3 into half sine 2t minus 4 by 3 cos of 4t plus 10 by 3 into 1 by 4 sine 4t. So if you look at the answers, you will find that it is nothing but the standard form which we have seen before. Okay, now there are more methods left which we will cover in the next video. The most important one of them is convolution. Thank you.